All right, guys, so let's keep going with this problem. But what happened is that since we reset the problem, we're going to have different data, but the procedure should be the same. So basically, here we had a standard Brayton cycle, but for air, okay? And that's what we had last time. So this is the standard Brayton cycle. We have the compressor, heat exchanger, turbine, heat exchanger. Okay, and in this problem, we're given that the substance is air, and within the compression ratio, between the compressor, we're given the compression ratio between the exit and the inlet, so P2 over P1. And the first thing we needed to calculate was, I think was the power here, is to find the power of the cycle, okay? So if we go back, let's see what we did. So the first thing we did is to find the mass flow. We know it's steady state, so the mass is conserved. So using the data given at 1, the volumetric flow rates, we know the mass flow is density times volumetric flow rate, or just volumetric flow rate divided by the specific volume. We're able to find that the mass flow rate is 57.73. So the good thing about last time is that we did not have to interpolate. So maybe this time you're gonna have to interpolate. So anyway, so we consider the system only of the compressor and the turbine, because the overall work of the cycle will be equal to what? Or the power of the cycle will be what? The power generated by the turbine, but we know that some of the power generated by the turbine will be used by the compressor. So basically the overall power generated by the cycle should be what? Turbine minus compressor, no? Okay. So basically that's what we have over here. You see, when we apply the first law of thermodynamics to this control volume, there is no heat exchange. And we know that the work done by the turbine minus the work done by the power used by the compressor will give us the overall power. So we know M, the mass flow. We needed to find H1. So we found H1 just from the table directly. I think it was table 822, because we know the pressure and we know the temperature. Okay. Now for 2, we need to know 2 things. So what are the things we know? We know the compression ratio. And if you remember, we derived these isentropic relations, which is P2 over P1 equal PR2 over PR1. And we find the PR value from the table. That was 1.80889. So from here, we can calculate P2. And now, bad luck, we did not take the other values. But from the table 822, we needed to go and interpolate. And we found that T2S, I don't think would be needed, is 649.3. And that H2S was equal to 659.13. Okay. So now, what else do we need? We have H1. We know H2S. Oh, we know we need H2S for what? For the efficiency, and that's where I think we had the issue. Okay, so let's say page. Okay. All right, so let's say this will be page 1 for today. That way we don't get lost. Okay, so instead of going back and forth on the notes, I'm going to get crazy. Let me just look here at the expression, but I think it was the H2S minus this expression here. So this, remember, this is the solution. So what is the efficiency? So last time we had these values, which was good. Oh, do they have the correct values here again? Or I don't remember. But what is the efficiency of the compressor? You see is H2S minus H1. So right down here, compressor efficiency. That's because we don't need H2S, we need to find H2, no? So compressor efficiency write down is H2S minus H1 divided by H2 minus H1. And I think that's where we stopped the other day. I don't know why we cannot find those notes. Okay, so we have this equation over here. Oops, what happened here? All right, just put the light. So we have this equation, which will mean what? That, okay, so if you want, let me just do a little bit of algebra. We'll have H2 minus H1 will be equal to H2S minus H1. With this, is going to give us what? H2 minus H1 equal to H2S minus H1 divided by the efficiency. So at the end, we find that H sub 2 would equal to what? H sub 1 plus H2S minus H sub 1 divided by the efficiency of the compressor. So if we do the numerical application, we should get what? H2. So we found H1 to be what? 280.13 plus H2S. We took the solution from the book, 659.13 minus 280.13 divided by the efficiency of the compressor, which is 92%. So it means 0.92. So I don't think the solution we have this data, but we can check. Maybe we are lucky enough. Otherwise, do that calculation for me, please. So you see, this is one from the class notes. Same expression. So this should be, is that the same value, T2S? You see, it's a different data, this one. Compression ratio is the same. Temperature is the same. What is different on this one? Oh, that's the one we had the other day. So I won't be able to give you the values, but can you give me the value for H2? Should not be that off from this one. Okay, so this is the value they gave me, but go ahead and check. So we're here, we go here. So here we have the compression ratio. This will have a similar compression ratio. So now we need to go to what's happening here. So we know H1, H2, we need to find H3 because it's needed over here, H3, okay? But let's see, what do we know about H3? So I think we're missing some information here, T1. Okay, I think we're missing some information. Let's go back. Hopefully we're missing something here. So you see here the compression ratio is 17.5. Okay, so this is the highest temperature. Do you have the value we had last time for the highest temperature? Did somebody write it down? It's probably the one on the solution. So let's see. I think last time they had, you see 2100 for the T3, no? Probably they were seeing the highest temperature was T3. So why is T3 the highest temperature? If you look at this figure, what's happening here? You go to the compressor, what's going to happen on the heat exchanger? You heat the substance that is going through, no? Okay, so T3 should be the hot temperature. So we know T3. So let's put here or to find H3, we know T3 we say will be equal to 2100. I think that's the one they use here. Yeah, so 2100 Kelvin. We go to table A22. And from there, we're gonna get H3, and we're gonna need also PR sub 3 to do the same thing as we did over the compressor. So here we go. All right, let's go to the book. Okay, so that's table A22. We go to 2100. So we need the second value and this one on the column. So 2100 is right here. So 2100, we have H equal to 2377.4. Correct me if I do something wrong. 2377.4. And PR3 in that case will be 2559. Okay, so we know H3. Okay, so now the last one to find is to find H4. Okay, the last one we need to find is H4. So in order to find H4, okay, so we know that I'm going to do the two pictures here. I'm going to explain this, just redo the figure very quick. Okay, so this is just for the understanding. If you want, you don't have to do it. This is compressor. This is turbine. And here we have 1, 2, 3, 4, and this one other heat exchanger and heat exchanger. Okay. What is something peculiar about the heat exchanger? Is that they work at, is it a change in pressure in the heat exchanger? No, so they work at constant pressure, no? So we could write over here what? P3 equal to P2, and this works at constant pressure, so you could also rewrite what? P4 equal to P1, no? Okay, and what do we know? P2 over P1 in this part was equal to 20, okay? So from here, what can we have? That means that P2 over P1 equal to P3 over P4 equal to 20. And what is the isentropic relation that we used earlier? So we had the relation, remember P2 over P1 we used was equal to what? PR2 over PR1. So over here we could say what now? This is also equal to PR3 over over P4 equal to PR3 over PR4. So that means what? PR4 would be equal to what? Would be equal to PR3 times P4 over P3. So basically, make it complicated to make it easy. If here, this is if you compress here P2 20 times P1, what's going to happen over here? The pressure at P3 is 20 times the pressure at P4, no? So here there is an expansion, no? Throughout the turbine. So we do the numerical application over here. We're going to get PR4 equal to PR3 that we got from the table 2,559 times what would be P4 over P3 should be equal to 1 over 20. So what do you get for PR4? Okay, somebody asked about what is the PR, difference between PR and P. So basically, if you remember from the change of entropy, we had this expression over here. Right? I don't know if you remember or not, but this is the expression. So if we are dealing with an isentropic relation, what does that mean? That the change in entropy is 0. So if you this equal to 0 and solve, you can solve now for the ratio P2 over P1. We're doing some basic algebra, okay? We find P2 over P1, which is equal to this relation, and that is what the PR2, PR1 are, these values. So PR2 is not the same thing as P2, and PR2 really doesn't have a big meaning, but what is interesting is what is that the ratio of the two PR2, PR1 is equivalent to the ratio of P2 and P1. Okay? And in the tables, what they give us is this ratio over here. So we can use, if we know the ratio of the PR values, we can find what would be the value of the pressure. But it was coming from this derivation over here. Okay? So now, which I'm going to let you do it, how do we find H4? We need to go to table 822 and interpolate, no? Okay, for this one, which is 1,254.5. So we go here, 1,000, let's see, PR, 1,000. So it looks like it's going to be between 1,750 and 1,800. Okay, so I'll let you do it. So I'm going to write here, interpolating. From table 822 between 1,750 and 1,800. You should be able to give me the value of H4S and T4 or T4S, as we had before. I don't know if we're going to need those temperatures, but on the previous interpolation, they give us the T2S, so go ahead. Yeah, guys, so this calculation, I was doing on my head, but I forgot I was 50 behind, so it's 1,279. So maybe now it's going to be different temperatures. So good call. So if this is 1,279 now, what are the temperatures we need to interpolate? So it's 1,279. We're still lucky, still between the same two temperatures. Okay. So go ahead. I'll give you time to do the interpolation.
It is 127.95. It's not 1279.5.
Okay, so What is it?
It's the same number, but it's 127.95.
102,79.75. Okay.
No, the one goes before the 9.
I mean, tell me one number at a time, okay?
Okay, 127 point.
What do you mean point? Oh, point, okay.
95.
Oh, okay, so it's a huge difference. So if this is the value, yeah, I divided by 2. I forgot to, I was also doing by 2. So sorry for that. So it's 127. So here we go. So completely off. So we need to look at this one of 127. This is the PR. So 127 will be between 1020 and 1040. Okay. So this is 120, 140. Okay, guys, so after the interpolation, we get that H for S equal to 179.4 and T for S equal to 129.2. And now what do we know about this system here? We know that the efficiency of the turbine is 95%. And the efficiency of the turbine, hopefully is in here, is given by the relation. So hopefully this time we don't do a mistake. So it will be efficiency, so turbine efficiency. So be careful here because our 1 and 3 will be different. So our 1 is 3, no? It will be H3 minus our 2 will be the axis, so it will be H4 divided by H3 minus H4S. So hopefully, so this is what I have over here. So basically we do some basic algebra. This is going to give us that the efficiency is H3 minus H4S equal to H3 minus H4. Or from here, we can get that H4 will be equal to what? H3 minus the efficiency of the turbine times H3 minus H4S. I want to put H4 on the here. Okay. 7. So 6, 7, this should be 8. Yeah. So if we do the numerical application, let's see what we get. We'll get H4 equal to H3, which is 2,377.4 minus the efficiency of the turbine, that is 95%. So 0.95 times H3, 2,377.4 minus H4S, that we found to be equal 1,079.4. Okay, so now we got the value for H4, meaning that we have all the data now to find what will be the work of the cycle, which is this expression over here that we had on page 6. So let's see over here, let's write, recalling. that the total power of the cycle will be equal to m dot h1 plus h3 minus h2 plus h4. So this will give us what? So if we do the numerical application, we initially found that m was equal to 57.93 59.73 kilograms per second times. So H1, we found H1 to be, let's see what that is. H1 is 280.13. H3 is 2,377.4 minus H2, we found H2 to be 779.04 plus H4 is right here, 1144.3. And all these should be kilojoules per kilogram. So we see that the units are okay because we went down with kilojoules per second, meaning that this should give us kilowatts. All right, guys, so let's go back to the equation. Looks like here, when we did the numerical application, this calculation wasn't done properly. So supposedly this is equal to 690 point what?
690.08. 692.08.
So 690?
692.08.
Okay, 0.08. So this would be for H2. So now for H2 should be this term over here. So this term is 692.08. And if you use now this data, what do you get for the power of the cycle? Okay, so you do this, gives you approximately 49.04 10 to the 3 kilowatts. Okay, so again, guys, remember that important part here is the procedure, the numbers. Easy to do a mistake, no? So next thing we need to find is the Q in. So I don't know if we have done it already. Looks like not on any of my pages, but basically what do we need to do? We just need to consider the control volume of this heat exchanger on top, okay? Between 2 and 3, so let's say considering the heat exchanger between 2 and 3, that's where we have the Q in. And this will be our control volume. If we apply to this system the first principle of thermodynamics, what do we get? Q dot minus power plus m dot H2 equal to m dot H3, we know there is no work or power done over here, so we're gonna get Q in is equal to m dot H3 minus H2. So if we do the numerical application, we get Q in equal to 59.73 times H3 is equal to what? To 2,377.4 minus H2 is the 692.08. Okay, so here I kind of look, this is not the result, but this should give you 10.07 megawatts. Approximately, okay?